Okay, we're going to look at algebraic expressions, properties of numbers, and the distributive property. We've already done quite a bit with properties of numbers in previous courses, and we talked a little about the commutative property in a previous session. Before we get into it, let's take a look at this. Have you ever felt like this? Most of us have, I think. Just a darn minute. Yesterday you said x equals 2. It is confusing when you first encounter this, isn't it? But today we know that x is an unknown, right? So we put x in there to represent an unknown. Well, my handwriting, I guess I better resort to the pen, excuse me. X is an unknown. And we use it in many different expressions, and it could actually stand for many different values. Please realize that every time we have this 5 minutes, this is a review. You can skip over it. It oftentimes takes me more than 5 minutes to get through it. It's helpful if you want to make sure you're okay with the previous lesson. Today, we're going to just look at some of what we've done previously. In the case of this expression here, we've got a -5 and we're subtracting a +7. I like to convert these all into addition problems. So we've got -5. If I want to convert this into an addition, I have to take the additive inverse of a +7, which is a -7. So I'm adding a -5 and a -7. They're both the same sign. So that'll be a -12. This one is already in the form of adding the additive inverse. So I've got a +7 and I'm adding to that a -4. We find the difference between them and take the sign of the larger, which is positive. So I end up with a +3. Here we have multiplication. One of our factors is negative. One of our factors is positive. We know that our result, therefore, will be negative. It'll be a -42. The next, again, is multiplication. This time, they both have the same sign. We have two negatives. That will always lead to a positive product, in this case, 20. Here we have another multiplication. One of them is negative, the other one is positive, so we know in the end we're going to have a negative product. Remember now, multiplication is actually much simpler with fractions than addition. With addition, we would have to have like terms. These would have to have the same denominator, least common denominator. This is not addition, so we've got an easier situation. This is multiplication. All we need to do here is to multiply the denominators together. And multiply the numerators together. There's our answer. This next one is a division problem, but I prefer to work it as a multiplication. You remember that. Stay, change from division to multiplication, and flip. Take the reciprocal. So we have a -4/5 times So let's stay, change to multiplication, and flip. One negative, one positive. Our result, our product, will be negative. Be negative 12 over 55. And finally, the area of a rectangle with width W and length L. We know we can find the area of a rectangle by multiplying the length times the width. So what is the area of a rectangle that has a width of 5 and a length of 7? Now, to just write 35 isn't entirely correct. 35 is the right number, but we should pay attention to the units. We don't know what the units are, so in this case, we can't square inches or square centimeters. Those aren't given. So we're just going to say units squared, and that would be the proper answer here. That completes our review. Let's get into it. Algebraic expressions, they're composed of numerals such as 1, 22, 107. They're also composed of symbols. We could have division symbol, plus symbol. They're composed of constants. Actually, if you have a term which has numerals in it, those are constants. And we also have pi as a constant, right? It has a very specific number. You've studied this before. It just goes on and on and on. Then we have variables. What's an example of a variable? X, Y. We could use A, B, or any letter we like to represent an unknown. In the expression 3m plus, how many m's do we have here? 1. All terms have a numeral coefficient. This one is 3 for this term, and what is it for this one? It's not written, but we know what it is. It's a 1. We don't usually write that out. Can the first m, this one right here, equal 3, while the second one equals 2? Is that allowed? No. Whatever m is, it is the same in all instances of the expression or an equation. If we actually needed this to take on a second value, then we would use another variable. So the answer is no. In the expression x plus y, can x equal 2 and y equal 2? Certainly. It's kind of a coincidence that they're the same, but there's nothing to prevent them from being the same. Let's evaluate these quickly. 3 times x minus 7. We're going to substitute in a 4 for that x. Looks good. Now, a negative 1 times a negative, whatever x is. Notice how I isolated the negative from the value of x. That's an important thing to do to keep yourself out of trouble when you start handling the negatives. And I'll show you. In this case, it is important, because we're going to say x is equal to a negative 3. So just this piece right here, That's my x. So my x is a negative 3. Oops, negative 3. If we are subtracting, we got a negative times a negative. Whew, that becomes a positive, right? So I've got a negative 1. That didn't change. But negative of a negative becomes a positive. I end up with negative 3 is my answer. I know these are kind of simple examples, but they illustrate some fundamentals that I think will keep us out of trouble later. Here I've got absolute value. Please think of these absolute value signs as a type of parentheses. When you're considering the order of operations, parentheses, you handle anything inside parentheses before outside. E, exponents, multiplication, division, and then addition and subtraction. Multiplication, division, addition, and subtraction. So these two brackets, we do whatever we need to do inside of these before we do anything else. X equals 5, okay. So a positive 5 and a negative 7, we find the difference between them. Take the sign of the larger, which is the 7. So that's negative 2. We know what absolute value does to an expression, right? It strips away its negativity. Wouldn't that be nice if we could just do that to anything that was negative? Just apply the absolute value function to it and strip away the negativity. All right, here we go. We're going to look at some of the properties. You know these properties already. This one, for example, we talked about. 3 plus 4 is the same as 4 plus 3. What are we looking at here? The 3 has commuted from its first position to the second, and this has commuted from the second to the first. So yes, whoops, we know what this property is. This is commutative property. On this one, we've got 2 times 4 times 3. 2 times 4 times 3. The positions are exactly the same, so we're not talking about commutative. What do we see that's different? All the parentheses are doing here is associating the last two terms, and here associating the first two. So no surprise to us, this is the associative process. Now finally, the adding the 0. What happens to 5's identity when we add 0 to it? That's right, nothing. It stays the same. So this is the identity property. So commutative property relates to the position. Associative property relates to how things are grouped. And the identity property is interested in whatever you started with being the same after you have applied the identity property. You add a 0, you still have the same identity. Now we're going to do a few little examples. What property are we illustrating here? Well, we're talking about addition. Oh. This was at the front, and it is now second. This was second, and is now in the first place. So what do we have here? Commutative. Has changed position. Is this expression equivalent to this expression? Let's write it out. 3x minus 3. Is that equivalent to a negative 3 plus 3x? What's happened here? The only thing that's happened is they have changed their positions. So the answer is yes, that's the commutative property showing up again. Is 3 an acceptable replacement for this expression? Remember now, it's not asking you if 3 is an acceptable replacement for x. That's not what it's asking. It's asking about this whole expression. Well, one way we can test that is to take that expression and see what happens if we set it equal to 3. Will this turn out to make any sense? We are dividing by 3x, so to simplify things, let's multiply both sides by 3x. That'll give us x minus 3, and then 3 times 3x equals 9x. Then we'll subtract x from both sides. We're going to have 8x equals negative 3. And I divide both sides by 8. X equals negative 3 over 8. That looks perfectly reasonable. So our answer to this question is yes. A divided by B. Well, let's look at this side of the equation with an equivalent expression of A times the reciprocal, right? Stay, change, flip. A, we changed from division to multiplication, and we took the reciprocal. Does that equal, stay with B, change to multiplication, take the reciprocal of A? It might be a little clearer if I wrote it like this. Is that true? Well, we probably could use numbers that would make it true. So it could be true. But in a question like this, we're interested in, is it true all the time? So if I can think of just one instance where it is not true, I would say no. And I can think of one instance. Suppose A is equal to 1 and B is equal to 2. Those are good numbers. Then I would have 1/2 is equal to 2. That's not true. So my answer here has to be no. And you know what else that tells us? That when you're talking about division, it is not commutative. Not commutative for division. Okay, finally, if you say x divided by x equals 1, what else do you have to say? Can never divide by 0, right? So this x cannot equal 0. Let's review the properties, and we're going to look at the properties for addition and multiplication. There are a couple other operations we've been talking about, and what are those operations? Subtraction and division. So these properties are not applying to subtraction and division. They're applying only to addition and multiplication. The commutative property works for addition. They can swap their positions. It's still true. Works for multiplication in the same way. The associative property, you can group them differently, but they still are equivalent. The identity property. We looked at the identity property of addition, which is 0. If I add a 0 to 5, it's still a 5. The multiplication identity is 1. If I have 5 and multiply it by 1, it is still 5. It maintains its identity. Inverses we've been talking about. What is the opposite of addition? Subtraction. What is the opposite of, and when we say, so the inverse for addition, we're talking about using the opposite sign. Inverse for multiplication, we're talking about division, and that's going to be flipping a fraction, right? And of course we can make anything into a fraction. For example, if we want the multiplicative inverse of 2, then we're going to recognize that it can always be written like this, and when we take the reciprocal, that's what we have. So let's bear these in mind as we go forward with some little examples here. Rewrite as an addition. So I have to write it as an addition. I can do that by taking the additive inverse of 4, which is changing from x minus a positive 4 to x plus a negative 4. Rewrite as a subtraction. Well, that's an unusual thing to do, but why not do it? It's just an exercise to make sure we understand things. This is saying x plus a positive 3. If we want to think of it as a subtraction problem, we've got to take the additive inverse of a positive 3, which is a negative 3. Commutative property of addition. So where things are located relative to the adding. So that would be our first term is going to become our second, 2ab, and our second term is going to become our first. Commutative property of addition. Now the commutative property of multiplication. This time, instead of looking at terms like we did with addition, things that have an adding or subtracting sign between them, we're going to, we couldn't use a subtract, excuse me, I misspoke, because the commutative property does not work for subtraction, only works for addition. Commutative property of multiplication. This is going to be our first term. This is our second. They're going to change positions. Commute. And there we have it. Now the associative property of addition. So it's going to look exactly the same as far as the position goes. We're not commuting. We're just leaving everything in the same position. So we've got 7a plus ab plus c. But we're going to associate differently. Instead of having these two associated with one another, we're going to associate the first and the second. So that's the associative. Associative property of multiplication. Again, the position isn't changing, nothing is commuting. So we've got three factors here. We've got an 8, we've got x cubed, and we've got y squared. We're going to use the associative property. Instead of associating the 8 and the x cubed, we're going to associate the x cubed and the y squared. Use the commutative and associative properties to justify this claim. So here's where we're starting, and we want to end up over here. Yeah. Well, one of the things I notice is that the commutative property has been applied right here. So this was a times 5, and over here it's 5 times a. So why don't we start with that? We're going to have the 5 and the a take a short commute, and we'll leave everything else the same. Now, what should I do next? I think I ought to maybe associate differently. So I could have, still in the same position, 5a plus 3 plus b. But instead of associating the first two, I'll associate the last two. Now, I might have this expression and this expression, which being added together, I'll apply the commutative property, and I'll end up with 3 plus b at the beginning, and my 5a at the end. Now you see that's lining up pretty well. 3, b, 5a. What's yet to be done? I'm going to use the associative property again to change the association. So my positions are good. 3 plus b plus 5a, but I'm going to associate differently. Write an expression equivalent to 3/5. We know the multiplicative There's a lot of vocabulary for you to learn here. I do expect you to know it. The multiplicative identity, we can multiply anything by 1 and it stays the same, right? It doesn't lose its identity. So I'm recommending here that you use 7 over 7 as your 1. I like to refer to these as fancy ones. They're equivalent to 1, but they look a lot more interesting. So we're going to take 3/5 and we're going to multiply it by 1. I'm not going to use just a plain 1, we're going to use a fancy one. 7 over 7. We know when we're multiplying fractions, we multiply together the numerator and we multiply the denominators. And everything was positive. There's another identity we could have done, write an expression equivalent to 3/5. We could have said, okay, 3 over 5 plus 0. That would be using the additive identity. Instead, we used the multiplicative identity. Number 9. I see a fancy 1 stuck right in there. A over A is equal to 1. So that could be simplified down to 3 over 6 B over C. And my 3 and my 6 have a common factor, don't they? So here again, I've got a fancy 1. It can be simplified, end up with B over 2C. Number 10, show that AB minus AC is the same as E. Okay, here's my AB. And I've got a negative AC, subtracting AC. So the difference in these two expressions is right here. That's what's been added in the middle. A minus BC plus BC. Well, what happens if I add those two together? A negative 1 and a positive 1 of these? Agreed? So this is equivalent to AB minus AC plus this whole thing, 0. So that is the additive. Identity. It doesn't change the value. So that's all equal to AB minus AC. Minus. There, it's proven. Now we're going to move on to the distributive property. I think you probably know this so well, because usually students have spent a lot of time using the distributive property. The only thing that sometimes gets us tripped up is in the end, when you start working with like terms. You have to remember what like terms are. Write the inverse of a sum. Yeah, that might be something a little bit new there. So, ooh, wait a second. Let's look at this cartoon here. Oh, what do you suppose they're demanding a recount of? Hint, 9 lives. Okay, here's our little review session. We know what to do, don't we? If we were going to distribute, we'd do that. There's another way we could handle it. We could say, well, inside my parentheses, a 4 plus a 7 is 11, which is equal to 55. But since we're about to talk about the distributive property, let's see what happens if we'd done this. We'd get 5 times 4, which is 20, plus 5 times 7, which is 35, so either way, we get to the same end. Let's try it here as well. If I subtract 2 from 8, I get 6. So this would be a 42. If I think about this in terms of distributing, I would have 56 minus 14, which turns out to be 42. Let's evaluate this expression. If I've got x is equal to 6, we're saying 3, and instead of x, I'm going to put in a positive 6 plus 5, which is equal to 3 times 11, which is equal to 33. And if I had used the distributive property instead, what would have happened? I would have had 18 plus 15, which is 33. Let's evaluate this one. We've got absolute value. My x is equal to 2, and I'm going to be subtracting whatever I have for a value of y, which is 4. So that's the absolute value of 2 minus 4. It's the absolute value of negative 2, which is always negative gets stripped away, 2. Simplify this expression. Have a fancy 1 in x over x. So I've got 4y over 2. But there's a common factor here. 2 times 2 is my 4, and 2 times 1 in the denominator. I have a common factor, which is equal to 1. My answer is 2y. I could write over 1, but we typically, when we get our denominator down to a 1, we don't bother writing it anymore. Factor 91 into the product of two numbers. Okay, so here we want to see what will divide evenly into this. Could I divide this by 2? No. Could I divide this? We're looking for prime numbers. Could I divide this by 3? No. None of the even numbers are going to work. Could I divide it by 5? No. Could I divide it evenly by 7? Ooh, that shows some promise, doesn't it? 7 divided into 91. It'll go so 91 could be expressed as 7 times 13. So that is factoring 91 into the product of two numbers. Distributive property. Here we go. Our review is over. We're getting right into it. Oh, somebody made a mistake. What mistake did they make? This is so common. Distributed to the x and then forgot to distribute to the y. I want you to keep in mind the order of operations. This becomes important here. Now, I was demonstrating the distributive property before, but he didn't have to use it because back here I was able to add my 4 and my 7. However, in this case, these are unlike terms, y and 3. I can't add them. But we can distribute, and should. That'll give us 5y plus 15. This one, same thing. Distribute, and remember, you distribute to everything inside the parentheses. So you end up with RA plus RB plus RC. Here we have a -1 and an A, right? We are going to distribute both the -1 and the A to the two terms inside the parentheses. That'll give us a negative AZ. And when we say -1 times a positive 2, a negative 2A. And finally, number 4, we're going to be distributing a -5 and an X. So we'll end up with -5 times a positive 1 gives us a -5. And the X times the X will give us, X times X is the same as X squared. We'll talk more about that later. A -5 times a -7 will give us a positive 35. And X times 1, let's So there we are, the distributive property. Factoring is the reverse of multiplying. Back here on the previous page, we are multiplying. When we factor, we're taking things apart. So we're going to do the reverse of the distributive property. So we're going to think about what we can take out of here. Well, we can see a common factor, 9. So we divide this by 9 and this by 9. It leaves us with x plus y. The way we can prove to ourselves that we didn't make a mistake is to distribute it back and see if we end up with the same thing. Okay. What do we factor out of this? What's common? A common factor between 18 and 21. So if I divide this by 3, I end up with 6a. And if I divide this by 3, I end up with a positive 7b. And if we're a little unsure, we check it again. Say, okay, if I distribute this, I get 18a and 21b. Okay, that looks good. How about this one? Do we have something common that we can factor out? You bet. We have an a. Remember, although we don't usually write it, this does have, as all terms do, a coefficient of 1. So when I divide both of these terms by a, that's factoring a out, I am left with a 1 here. A lot of people forget that. A divided by a is going to be equal to 1. If I were subtracting, I would get a 0. But anytime you're factoring, dividing, you're going to get a 1 plus 3y. How do you know if you've got like terms? This is the definition. Take a moment to write it down. Terms must be identical in these two ways. They must have exactly the same variables, and the exponents also have to match. So let's see. Identical variables. So the variables in this expression are x and y, and in this one are also x and y. Do the exponents match? Okay, for x, they've got a 3 in both cases, so that's good. For y, so yes, these are like terms. Are you wondering about the 3 and the 5? They're okay. That's not part of the definition of like terms. In fact, if you want to think about it this way, we're talking about, let's call this expression right here, x cubed y squared, as a critter. X cubed y squared critter. We've got 3 critters and we've got 5 critters. You could see that you could add those together. We know what we'd get. Of course, we'd get 8. So let's look at this one. Here we've got x in this, and x in this one, y and y. So far, so good. The exponents must also be the same. The exponent isn't written here, but we know it's a 1. We never write 1 when it's the exponent. But we run into trouble here with y, don't we? Because this one, the exponent is 1, and in this term it's 2. So no, these are not like terms. How about these? Oh, these are looking pretty well matched. All x's. Identical variables, so it checks with that. Exponents. What's the exponent on this one? That's that unwritten 1. This one's a 2, so we don't have a match. And this one doesn't match to either of them. So this is definitely a no. All right. Negative 3x and 3x, are those like terms? We're going to use our definition. They both have x, so the variables match. And their exponents, we don't see anything there, but we know it's the unwritten 1. So that's a match. Variable and the exponents match, so the answer is yes. These coefficients, they can be as different as anything, as long as they're numbers. Let's see. Are these two like terms? Well, this has an x and this has nothing. No, those do not match. Those are not like terms. Collect like terms. Okay. All three of these terms have x, so they match for variables, and the exponents on all of those are the unwritten 1. So those can be added together. 5 plus 4 plus 2, 11x. Let's try this one. This one's got an A, this one's got an A. This one's got a B, this one's got a B. So these two can be matched together, and these two. And we should do that, combine the ones that we can. 5a minus 8a is going to give us a negative 3a. A 7b minus 2b is going to give us a positive 5b. That's looking pretty good. Let's see how much further we have to go. I'm sorry about this. Quite long, isn't it? Inverses of sums. Multiplying by negative 1 will flip the number to its mirror image on the number line. So if I had, let's mark it on the number line. Here's a negative 1. And if I multiply it by a negative, it turns out to be a positive 1. So it did happen. It ended up right over here. Okay. And the same thing is going to happen with this. The negative, I'm going to distribute it in here. It's going to become a negative z, positive 7. What happens with this one? I'm going to distribute that negative to all terms within the parentheses. And I'll have a positive 3a, a negative 2b, and a positive c. I'll do that on this one, which has even more terms to consider. And I get a negative 9a, a positive 4b, a positive c, and a negative d. And what happens with this one? Same thing, I'm going to distribute to all the terms. And please notice this is just one term here. You can tell a term because it's divided away from the rest of the expression. It's separated, I should say, from the rest of the expression with either a plus or a minus. So this becomes a positive 1/2, a negative 2/3 x, and a negative times a negative becomes a positive 4/7 x squared. Are these equivalent expressions? Well, let's see. that becomes negative A, negative B. So the answer is yes. How about this one? When we put that in there, let's see what happens. We end up with a positive A and a negative B. So this is not equal. This is a no. Simplify this expression. That'll be 3A, right? Plus 5. These were like terms. See, I've got a like term here, here. So those can be combined. But I better be really careful here. Did you catch that? Oh, that's wrong. Let me get my eraser out. Yeah. Oh, I can't believe I did that. What did I forget to do? Here we're talking about the distributive property, and your teacher, Horace, forgot to distribute. All right? The negative goes to a positive A, making it negative. Negative goes to a positive 5, making it negative. And then we've got a couple like terms. I was so far off. Shame on me. There it is. In this case, it's even more conspicuous, to me at least. Just shows you how easy it is to make that mistake. We have nothing happening in these first two terms. They're exactly the same. But then we have a positive 5z becoming a negative 5z, and a negative 3w becoming a positive 3w. So we're going to combine the w's. I'm going to combine the z's. So a positive 2, a negative 5, negative 3z, a negative 4, a positive 3, gives me a negative 1w. I won't write the 1. Yeah. How about this one? All these negatives to distribute, I guess that's really good practice. You would never believe that I actually had constructed these myself. I come back to them later and I forget what I'm doing. Negative 4 times a positive z, a negative 4 times a positive 2. We've got like terms here and here. So we get a negative z, negative 8. Oh, look at this thing. We're going to have to do these next two in stages. Remember, we work from inside the parentheses out. So I'm going to distribute this negative 3 first. We'll have 9 minus 2. I'm not going to do anything to that yet. And I got positive 2 on the inside of the bracket. Then this will become negative 3 times a positive x, negative 3x, and negative 3 times a positive 1, negative 3. Now I really should combine any like terms that I can before I do any more distribution. So I'll say 9 minus 2. And can I simplify this? I certainly can, because here I have plain old number and a plain old number. Those are definitely like terms. And when I combine them, it's just going to be a negative 1. So I've got negative 3x, which was already here. I haven't done any distribution. I'm just looking at combining like terms. Minus 1. Now I can do some distribution and say I'm going to multiply everything inside these brackets by negative 2. So that's going to equal 9 A negative 2 times a negative 3x is going to be a positive 6x. A negative 2 times a negative 1 is going to be a positive 2. And I still have opportunity to combine like terms because, again, I've got some numbers. So I've got 6x plus 11 for my answer. All right, let's do this one. This one looks even more challenging. Starts with parentheses in the center of this nest and then comes out to brackets, square brackets, and then to curly brackets. So we're going to start with right in here. We're going to distribute this positive 2. At least we don't have negatives to complicate things in this one. I'm not going to touch anything outside of these square brackets, so let me just copy that whole thing over. A, and the opening, curly brackets, 3 plus B, square brackets. I'm not going to do anything with the C. Let me leave some room, because I am going to distribute this 2, and then the curly brackets. So a plus 2 and a plus D is a plus 2D. When I multiply them, multiply that, I get a plus 2. And there's no opportunity here for me to simplify those. All three of them are different from one another. They're unlike. Well, that's kind of a bummer. Now I'm going to distribute the B to everything inside the square brackets. I'm still not doing anything with the curly brackets. So I've got 4 plus A, open curly bracket, 3 plus, and now what do I get? BC, 2BD plus 2BD, and then B times plus 2, and closes with curly brackets. I'm almost finished with all these brackets. I again have no opportunity for simplification. Nothing to combine here. Every one of these is different from the other. And nothing's going to, this A is not going to improve things for us at all. Still all going to be different. But at least I can get rid of the brackets. So we're going to say 4 plus 3A plus ABC, I like that one, kind of catchy, isn't it? Plus 2ABD, be so easy to make some stupid error right here, plus 2AB. And I know a lot about stupid errors. I made plenty of them. Any opportunity for simplification here? Rats. There isn't. Yikes. All right, I'm just going to look at a closing slide. Oh, you've certainly put your time in today. We're almost at the hour mark. What did we add? We already had this one and this one, identity and inverses. We added the distributive property, which says that x factored out of this is the same as x times each of those terms. Ooh, well, thank you very much for hanging in there with me. That's a good review of some of your Algebra 1 stuff.